Hello again. Time for some more physics from me. So this is lecture for chapter 6. Chapter 6 titled Photons and Matter Waves. This is your introduction to quantum theory, kind of baby steps into quantum theory or how it came about. I mentioned in the relativity chapter that was sort of one major paradigm shift that happened in the early 20th century in physics, in our understanding of the universe, physical understanding of the universe in general. Quantum theory, or the quantization of energy and matter, is sort of the other main shift, paradigm shift. So we're going to get into a little bit of that today. As it turns out, our explanation of the quantum world, or quantum theory in general, does rely on some stuff from relativity, as you'll see a little later on in this lecture. Well, just to start out by showing you this cool image from an electron microscope, which, as I'll say at the very end when we come back to this image, is one outcome of our understanding of the quantum nature of matter. We're able to use electrons, and not just visible light, to make something like a microscope, and electrons allows us to look much smaller, or at much smaller things than your optical microscope would. These are pollen grains, I think. Yeah. Kind of have to do a little bit of a history lesson, in a sense, in order to get into where quantum theory came about, why it came about, and basically we're going to see a number of experimental results from different kinds of experiments, data that was around at the time of the mid-1800s to early 1900s that was rather confusing to a lot of people, a lot of physicists. People weren't able to understand why things were acting the way they were in certain areas. People had come up with formulas to quantify these results and reproduce them with the mathematical formula. There was no physical models underlying those formulas. There was no understanding of why those formulas are the way they are, or were the way they were. So we're going to look at a couple of these areas where classical physics was failing. The first one we'll look at, and what brought about the initiation of this idea of quantization, had to do with black bodies. One version of a black body is this sort of circular or spherical cavity that has just this tiny little hole so that light can come in, but light doesn't actually get back out. So inside of the cavity, it's all blackened and it's really rough. The light is absorbed by the wall, and more of it absorbs because it's black or darker. And then also it's rough, so the light is bouncing around in all these random directions. And the fact that there's just this tiny little opening means that almost no light is getting back out. In the idealized black body, there would be no light that got back out. No radiation could leave this black body once it entered. In reality, there's no such thing as a perfect anything, really. And in the case of black bodies, it means that some radiation does get back out. We're going to be looking at all these experimental results, and it's interesting maybe to point out that quantum theory arose mostly just from experimental data, or data that couldn't be explained with classical physics, whereas relativity arose almost as just an analysis of the results of a classical theory, right? Maxwell's equations basically said that light is going to travel the same speed in all reference frames, and Einstein just kind of took that and ran with it. So that, along with the invariance of physical laws in inertial reference frames, those two things give you special relativity. Right? Einstein wasn't like looking at light clocks and noticing that they were acting oddly or anything like that. Right? It was all sort of a theoretical push that brought about the special relativity. This is as opposed to quantum theory, which is weird things happening, trying to explain them. Okay, so if you have a black body, or something that's acting like a black body, at least that basically absorbs almost all the radiation that comes into it and just emits a little bit of it back, then you look at the light that is emitted by this black body, and you get these spectrums, these called Blackbody radiation spectrums. And they look like this. At essentially zero wavelength of emission, there's no radiation coming at that wavelength. As you start to go to longer wavelengths, the amount of radiation, or the intensity technically of radiation at those longer wavelengths, starts to rise and keep going to longer and longer wavelengths. Eventually that intensity of radiation is going to peak somewhere at some wavelength, and then it starts to fall off again. So to keep going to longer and longer wavelengths, the intensity of radiation gets less and less and less. This was just data, right? People had created these black bodies with these like spherical cavities and then been able to measure the intensity of radiation at different wavelengths coming out of those black bodies, and they knew that this was how things acted. And you also know intuitively that when you heat up something, it starts to radiate different colors in the visible spectrum, and more broadly speaking, at different wavelengths in the electromagnetic spectrum, right? So if you have like a piece of metal, say, and you start to heat it up, at some point it gets so hot that it starts to glow this kind of dull red. And if you keep heating it up, that red goes into becoming like an orange, and then like this kind of yellow. So that is to say that as you heat an object up, and the same for a black body, the radiation that is emitted from that object is going to keep shifting towards shorter wavelengths. So we see that these different curves here are, say, for an object at 2000 degrees Kelvin, right? That's the shortest one. That peak of its emission, that peak wavelength, is over here at 1.2-ish micrometers. You heat it up to 3000 Kelvin, that peak has shifted down about 0.9 micrometers. Keep heating it up, 5000 Kelvin, that peak, it's, I don't know, half a micrometer. All that is to say that the peak in this radiation spectrum, in this emission spectrum, was shifting to lower wavelengths as the temperature increased. And if you look also at the area under these curves, the area is increasing with the temperature in some way. The area underneath that 2000 Kelvin much less than the area underneath the 5000 Kelvin. So there's also a relationship between the area under these curves and the temperature. And since these are curves showing the intensity at different wavelengths, the full area under here is the power being emitted by those black bodies, or by these radiating black bodies. So again, this was experimental data. People knew these things and came up with formulas where you could quantify the relationships that I just told you about. Wien's law basically just said that the peak wavelength, the maximum wavelength of emission, is proportional to the inverse of the temperature, where it's inversely proportional to the temperature of that black body. As the temperature increases, the wavelength is decreasing, the maximum wavelength. And this is the full formula they found, and through fitting some of these curves, you could get this value. There was also this thing called Stefan's law, which told us that power, the area underneath these curves, is actually proportional to the fourth power of the temperature. And it's also proportional to the surface area of that black body. It's like the interior sort of radiating surface. The power also depends on that. Okay, so quick look at this example. We don't even really need to do any calculation. If we're looking at these stars in the constellation Orion, one of them is a little bit blue, Rigel. Another one, Betelgeuse, is a little bit red. Just from their color, we can tell which of these stars is cooler than the other, or which one's hotter than the other. So if you think back, remember at higher temperatures, the wavelength is shrinking. So the wavelength shrinking means it's going towards the ultraviolet end of the visible spectrum. When you're over towards the blue end, right, that's shorter wavelengths, that's higher temperatures. Meaning that whichever one was bluish, Rigel, is hotter than Betelgeuse. So Betelgeuse is the cooler star. So you had Stefan's law, you had Wien's displacement law. Both of those things were sort of fitting the experimental data, but again, weren't really based on any physical model or any theory, really. There was a model that was attempted to be made called the Rayleigh-Jeans model, or law, which took classical electromagnetism, right? It's electromagnetic waves that are just bouncing around inside of these black bodies, and if you use our classical electromagnetism and just say that that energy of those electromagnetic waves is being exchanged with the walls of that black body, the interior surface of the black body, you can do that and get a result for what you would expect the radiation intensity as a function of wavelength is going to look like. That's what they did. Turns out it fails miserably at small wavelengths. At large wavelengths out here, it actually gets fairly close But once you start going to short wavelengths, their formula essentially said that the intensity of radiation just keeps going up as you get to shorter and shorter wavelengths. And as you can see in the graph, that does not fit the experimental data that we have. The data there, I believe, is just the emission spectrum for some particular black body at a particular temperature. So beyond that line not fitting the data, if you think about it a little bit more, this law, Rayleigh-Jean's law, is saying that at shorter and shorter wavelengths, an object is going to radiate more and more energy. So for each smaller wavelength you get, you're getting more and more energy out. Which also means if you go essentially to a zero, like approach a zero wavelength, or think about infinitesimal wavelengths, then you're getting infinite amounts of energy out. If this was correct, then basically everything would be radiating an infinite amount of energy all the time, and the universe would basically just be on fire everywhere. That's not the case. I think that's pretty obvious. So this can't be right for that reason as well. This was called the ultraviolet catastrophe, because as you're going towards ultraviolet wavelengths, it was basically telling you that infinite energy was going to be coming out. So then along comes this guy Planck, Max Planck, who is trying to also make sense of this data, figure out how you could actually fit this curve. And he basically says, well, what if the energy that's being exchanged between the electromagnetic waves in that black body and the walls of that black body, what if that energy is discrete? It only comes in specific chunks, or specific amounts of energy. And there you go, quantum theory was born. Planck's hypothesis states the amount of energy emitted by the oscillator is carried by the quantum of radiation delta E. So a weird way of saying that the stuff vibrating in the walls of the black body that's absorbing or emitting this electromagnetic radiation, that's this oscillator, that energy is only emitted in chunks, this delta E. Planck worked out that that chunk had to be this h multiplied by the frequency of that radiation. So that delta E is like the change in energy of that oscillator, the tiny bit of the wall that's oscillating and emitting electromagnetic radiation back out to the interior of the black body. Right? So that's just that little change in energy. And if you think about, well, what is a unit of energy then? It's 1 hf, whatever that h is multiplied by the frequency. Energy then can be exchanged in increments of that unit. Right? So that's why you would say this energy in the electromagnetic exchange here is equal to some increment or some number of hf, or you could write that as n times h times f, and where n is now what we call a quantum number. Planck was able to use this hypothesis, and when you fit it to data, then h is this 6.626 times 10 to the minus 34th joules seconds, or also in electron volts here. So this is what we call Planck's constant. Sometimes I'll say Planck, sometimes I say Planck. I think technically it's Planck, but you know, I'm American, not very good at actually pronouncing things correctly. This is an incredibly small value, 10 to the minus 34th. So it's hard to overemphasize how different this is from the classical picture. In classical electrodynamics and in classical theory in general, the amount of energy that something can have, something like an oscillator, or electromagnetic wave for that matter, the amount of energy it can have is a continuous spectrum. It could have any energy. There's no cutting up of it. This is a big change where we're saying that actually there's a smallest amount that you could chop that energy up into. So instead of being a continuous spectrum, we would say it's a discrete spectrum. It comes in discrete chunks. So if you take classical electromagnetism and include that hypothesis, this energy exchange is quantized, then the radiation intensity of a black body is this. This is what you get out. And this is what Planck got out, and it fits the data perfectly. Funnily enough, it also involves Boltzmann's constant, which you might remember from thermodynamics, and the reason for that has to do with statistics, and it turns out that what we're talking about is probabilistic in a sense. So this number tends to come up when you're talking about things that are probabilistic. And apparently Planck just kind of thought this was a neat trick. It's a mathematical trick. You say energy is quantized in you manage to fit the data just as well as you can. It took some other people to kind of keep running with it. Right, so like I said, it's hard to overemphasize how different this is. And it's not easy to internalize once you first learn about this quantization thing. So try to come up with some analogies that might help. For one, you could think about what if bouncing was quantized. On our regular scale, imagine that a trampoline bouncing and the bounces on a trampoline were quantized. Let's take a look at what a normal trampoline bouncing looks like. Bounce, 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 bounce up, yeah. Got a kid lying down, two other kids that are, what you call double bouncing, but they're basically inputting energy into this kid who's like an oscillator on this trampoline. So you're inputting in this energy, and they bounce a couple of times and kind of get him going a little bit, and then hit him real good, and he just launches. If this was a quantized trampoline, then those little bounces wouldn't actually be able to transfer any energy. Only that big bounce is possible. Only that's a transfer of energy, right? So only that large transfer of energy is possible. That's the smallest quanta of bouncing energy you could have. So when these kids are doing these small bounces, they might be trying to bounce on here, but the kid in the middle wouldn't be moving at all. It would only be until the two kids on the outside are able to put in that right amount of energy that the kid would just get launched. That's an example of like a continuous energy being added versus this discrete energy, or discrete energy transfer. Another useful analogy or way to think about this continuous versus discrete thing is thinking about moving a box up some height. You could move that box along a ramp, where you just kind of push the box along the ramp. That would be a continuous change. You can move that box and it could be at any height along this ramp. That is as opposed to moving a box along stairs. If you want to move a box up the stairs, well, you probably pick it up all the way, but assume you can only have it on the stairs the whole time, then you'd have to take it from one stair to the next. That is a discrete change in that height. There's no in between. It's either this stair or the next stair, or maybe multiple stairs, but then that's just multiple units of that height change. So in this picture, the steps are essentially this energy quanta, this HF, right? And one step is like HF. And if you moved up multiple steps, it'd be like 3HF or 4HF. It goes back to that NHF equation. And as I pointed out before, H, Planck's constant, is incredibly small, almost unimaginably small, 10 to the minus 34th. What that means is that these steps are incredibly tiny. So if you imagine a stair where the steps are just kind of going towards zero almost, the height of those steps, then basically you get back to a ramp, right? Something that is discrete actually looks continuous. So when we're dealing with quantum objects, they tend to be incredibly small. And when you pull back to a sort of macro scale, all these tiny little weird stuff tends to even all out. Just like steps with incredibly short heights. Okay, so let's look at an example with some of this information where we're going to compare the energy of this macro scale, or the more sort of normal oscillator, to the energy quanta, or the minimum size of energy that could be added to this oscillator. So in order to look at the energy of this oscillator, we have to bring back, or think back to all the way when you're doing oscillators and like spring mass systems, back in the first part, for the first course, in this 3-part course. And if you did look back or think back, the energy in this spring potential energy, is 1/2 times the spring constant times the amplitude of that oscillation. You might look at this as like times y squared, but y, remember, would be the measure from the displacement from the equilibrium, and that's just the amplitude of this oscillation. So this is the energy in a simple harmonic oscillator. We put in some numbers then. They tell us that the spring constant is 1,000 newtons per meter. The amplitude is 0.1 meters. This comes out to be 5 joules. It's energy associated with this oscillation. Okay, what about then the energy quantum? Like, what's the smallest unit of energy that could be added or subtracted from this system? Well, it has to do with the frequency of this oscillation, so we need to know what the frequency is. And again, if you look back at simple harmonic oscillation for oscillators, it is 2 pi, or 1 over 2 pi times the square root of the spring constant over the mass of the object, which, put in those numbers, 1,000 newtons per meter over, they tell us it's a 1 kilogram meter mass, turns out to be about 5 hertz. That's the frequency of that oscillation. So what is then this energy quantum? Well, H times F. Remember, H is this 6.626 times 10 to the minus 34 joules seconds, 5 hertz. The frequency, that comes out to be about 3.3 times 10 to the minus 33 joules. So this is the smallest unit of energy you could put into this oscillator. That is the energy that the oscillator has right now. This is almost nothing compared to that, right? So the steps in that energy change that are possible, this smallest step that's possible, is unbelievably small compared to the energy of the oscillator. And this is true in general for things that are macro size, or our scale, and even down to micro size, but not, quantum sort of scale. So if you're asking yourself, like, why don't we notice this quantization of energy on our regular scale? Well, the amount of energy in this oscillator already is 10 to the minus 33 times larger than the amount of energy that can be added or taken away. So if you think back to that stair ramp analogy, but that 5 joules is like the height of this staircase that we can move up and down. 10 to the minus 33 is like the height of each of these steps. So there are steps there, but as far as anyone is really concerned, for the most part, it's basically a ramp. You don't see those discrete energy steps. Okay, Planck used his quantization hypothesis in order to make sense of the blackbody radiation. So here we have another place where physicists were getting results from experiments and they just weren't making sense in terms of our classical understanding. This is known as the photoelectric effect. If you shine light on metals, mostly metals, other stuff happens too, but mostly known with metals, then you can essentially eject electrons off that metal. So by shining some light, you knock some electrons off. That's the basics of a photoelectric effect. If you have this setup where you take your material, your target material, and put it into this vacuum chamber so you don't get any interference with gas in the air, and then set up another plate here, and then connect each side to a wire, right? Connect them together so you have this circuit. There's just this gap here. You start shining light on that target, then you're ejecting electrons, and those electrons are moving to the opposite plate, so you end up getting a current flowing in between these two plates, and then a current can flow through this whole thing. So you basically shine light on this thing, and you start to see current in that ammeter. This was a known phenomenon. People had measured things about it, but it didn't really make sense what they were seeing based on classical physics. It turns out that in order to explain this phenomenon fully, we need quantization of energy, like Planck was talking about, and we need photons, chunks of light. Right, first think about this situation in terms of classical physics. So you're shining light, so electromagnetic wave, onto this metal surface, and you're knocking electrons off that surface. So the classical picture basically just says that the electric field that's oscillating in that electromagnetic wave is dumping energy into the electron. It's oscillating the electron around, and then if it can dump enough energy into any of these electrons, then those electrons will now get sort of kicked off the surface. A wave, an electromagnetic wave, classical wave, the energy that's being added to those electrons or being given to those electrons is just proportional to the intensity of that wave. So a classical explanation of this phenomenon would say that if you increase the intensity of that light, that's more energy, you should eject more electrons from that surface, right? More charge from that surface. That means you're moving more charge across this gap, it'll be a larger photocurrent. Call this a photocurrent because it's due to this light causing this current. Also in the classical picture, at higher intensity, right, more intense light, again, would be more energetic light, means that you would be giving each of these electrons more energy to be ejected with. That is to say that they're going to leave that target material generally with more kinetic energy. They're going to leave faster if you shine higher intensity light on that target. Also increase the photocurrent in that way, right? Because current is made up of moving charge, so more charge, or faster charge moving, or both of them should increase the current. That's the idea from the classical point of view. And it should be noted that in the classical picture, the frequency of this light, its wavelength, doesn't come into the picture. It doesn't matter. Okay, so you can do some experiments with this setup, where one thing to do is to insert basically a voltage source into this circuit, and if you insert it in this way, that is shown here with the positive side on the right, you can create a field inside of that vacuum tube, right? The way it's pointing now, the positive side's on the right, so you would set up an electric field inside of this vacuum tube. You basically have this like capacitor, and you're going to set up an electric field that's pointing from the positive side to the negative side. It's going to point the direction a positive charge would move. So with the voltage source like this, the electric field will be pointing to the left here, meaning that the electrons, since they're negatively charged, are going to get an electric force on them to the right, and they're going to be accelerating. So with the voltage source in this orientation, you're going to actually add to the kinetic energy of these electrons that are being ejected from that target. But if this is an adjustable voltage source, and say we start cranking it the other way, bring that down, 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 eventually until you flip the direction, flip the polarity, so it's now positive on the left and negative on the right. Now we're going to have an electric field that's pointing from the left to the right. Right? So electric field pointing this way, meaning the electrons are actually going to feel a force in the opposite direction. Remember, they're negatively charged. So any electron that gets ejected is going to start to feel a force immediately that's pushing it back towards the target when we've flipped the potential here. Then if you keep upping that potential difference, right, now the positive side is on the other side here, and we're acting against these electrons, if you keep upping that, eventually there's going to be such an electric field set up inside of here that the electrons are not going to be able to leave the surface at all. Right? Even though the light's coming in, it wants to eject them, but even the one that's ejected with the most energy, that maximum kinetic energy that it's going to be ejected with, is equal now to the electric potential difference in the opposite direction. I hope that made sense. The book tries to explain this too. I don't know if either of us did that great of a job. But the end of that thought process is basically that you can measure the maximum kinetic energy of these electrons being ejected, because if you change this potential enough, you just stop those electrons altogether, and so that electric potential energy is going to be equal to the maximum kinetic energy of the electrons. And so once you get to that point, you've stopped all the electrons from leaving that target, even though the light's shining on it. That's what we call the stopping potential. People knew of this effect. They're measuring it, experimenting with it, and they could produce plots like you're seeing here, where you're plotting the photocurrent that's going around that circuit and the potential difference of that voltage source that you put into the circuit. When the voltage source was positive, you were basically kind of adding to the kinetic energy of the electrons, so you're getting a lot of this photocurrent. But once you make that potential difference negative or opposite the direction that those electrons want to go, then you're decreasing their kinetic energy. Potential difference is kind of canceling out their kinetic energy to the point where the photocurrent just stops entirely. That's that stopping potential. The problem that people had, though, was for classical waves, the energy that you're giving to those electrons, remember, should be proportional just to the intensity of that light. So the maximum kinetic energy that an electron would get is also just proportional to the intensity. Meaning, this stopping potential should definitely depend on the intensity of the light. But this was the experimental data at the time. They knew that that wasn't the case. Regardless of the intensity of the light that you were shining on the target, you had the same stopping potential. Something else that was also known at the time is that if you decrease the frequency of the light that you were shining on that target, then eventually you'd also get no photocurrent. This is a plot of the maximum kinetic energy against the frequency of the light. You can think about it as the current that's going to flow versus the frequency of that light. But if you think back, classical physics said that the current, the photocurrent, shouldn't depend at all on the frequency of the light. That's just not the case in reality, or experimentally, that just wasn't what they were finding. Decrease this frequency enough, eventually you get no photocurrent. The maximum kinetic energy of the electrons that are leaving that target is 0. They don't leave the target. This is what you call the cutoff frequency, because you're cutting off that photocurrent. And just to be clear, this is a generic plot. Each material has its own cutoff frequency. Again, typically metals that we're talking about for the photoelectric effect. All these big departures from the classical picture were quite puzzling to people at the time, rather confusing, trying to understand why the photoelectric effect was the way it was, why the current depended on the frequency the way it did, why the kinetic energy of the electrons could be adjusted with that stopping potential the way that it could. It then took Einstein to come along. That same Einstein that we talked about in the last chapter, in terms of relativity, you might be getting an idea of why he's such a big name. But Einstein came along and basically said, Planck, you were more right than you knew. Planck, remember, just kind of thought that his idea of energy quantization was kind of a neat trick, mathematical trick. Einstein said, no, that's maybe just the way things are. It's not just that the energy being exchanged in this blackbody situation, right, that electromagnetic energy, that was what Planck was saying is quantized. Einstein takes that picture and says, no, it's actually light that's quantized. It's the energy of light that's quantized. And if you start to talk about light in this quantum picture, you're talking about chunks of light, or particles of light, and that's where you get the idea of a photon. It just goes back to Planck's energy quantization. Now, the frequency we're talking about is the frequency of the light, and the energy we're talking about is the energy of the photon of light, that particle of light, at that frequency. Which means that light itself only comes in these discrete chunks, basically amounts of Planck's constant. In terms of the photoelectric effect, what Einstein was saying here was that this effect is essentially an all or nothing sort of thing. Meaning that the photon either has at least the amount of energy that it needs to give to that electron, and if it does, it will give all of that energy to the electron and it will cease to exist. If it does not, it doesn't give any energy to the electron and it keeps going along. This is another point that's hard to emphasize how different we're getting from classical physics. This is very much now a discrete versus continuous picture. Either this thing happens or it does not. In classical physics, it's always this continuum. And another odd result from this is that if that photon has enough energy to eject the electron, right, it gives all of its energy to the electron, it ceases to exist, the electron immediately is ejected from the material, or at least from the atom that it's bound to, and instantaneously gains kinetic energy, however much extra energy that photon had. So that's another bit that's very different from classical physics. The electron goes from bound to this atom to instantly moving at whatever speed it's going to move at, off away from the material. Okay, so going back to this cutoff frequency then, have this plot again. We're just looking at the picture you would get if you plot the maximum kinetic energy against the frequency, and for two different metals here. So again, there's this relationship where you decrease the frequency, the kinetic energy decreases, to the point where eventually that maximum kinetic energy is 0. And it turns out that these were linear relations that were found between that maximum kinetic energy and the frequency. So if you fit that data to a line, then you're going to have a line, that's y equals mx plus b relationship. Then that line has this y-intercept. Right? So you extend these things, right? The maximum kinetic energy can't be negative in actuality. just have positive kinetic energy. But if you extend these lines down, then you see where this intercept is, this phi 1 and phi 2. So now if we think about that light coming in as made up of a bunch of photons, and those photons are either giving all of their energy to the electron or they're not giving any energy at all, the energy of any of those photons is h times the frequency of that photon. And we can now think about it as that energy that it gives, that energy of the photon, is going into the kinetic energy of the electron that it ejects, plus this extra bit of energy. So if you look at the kinetic energy plus something else, that something else we end up identifying with the amount of energy that it took just to get the electron away from its atom. So the electrons are sort of bound to their atoms or the material overall. There's a certain amount of energy that photon needs to have just to release that electron. If the photon has more energy than that, that energy goes into the kinetic energy of that electron that it ejected. And if we just turn this around, then we can write that kinetic energy as a function of the frequency. This is our line equation, y equals mx plus b. That b is now this minus phi. That phi is like the work that it took to get the electron away from the material, or out of the material. So we call this phi the work function, and it is just a particular amount of energy for a given material. If we think then about that limit where that photon that came in is just exactly the amount of energy that it needs in order to release that electron from the material, the kinetic energy that it would have is 0, then we could say that the frequency of that photon that came in is the work function of that material divided by h. That's where our cutoff frequency comes in, or that is the cutoff frequency. Okay, let's put some numbers to this stuff. So this work function, this phi, right, is this amount of energy that you need just to get an electron out of a material. So we just have a table here of some different metals and their work functions, right? What's that energy? For sodium, in terms of electron volts, 2.46 electron volts. Just to relate it to other kinds of energy you might know or might feel better about. In terms of joules, that's 3.94 times 10 to the minus 19th joules. Very small amount of energy. So if we think back to how a wavelength is related to a frequency, right, and that frequency is related to the energy of that photon, then we can basically rearrange some of those equations to get the wavelength of the photon that has this amount of energy, that has that 2.46 electron volts. Turns out that 2.46 electron volts is about 550 nanometers. Right? That's in the visible spectrum. There's a bunch of these other ones here, aluminum, zinc, iron. Off the top of my head, I'm not sure what PT is. Platinum? I don't know. But it has the largest work function at 6.35 electron volts. That's in terms of joules also. And then as far as the wavelength of that photon that has that energy, that's 195 nanometers, which is somewhere in ultraviolet, right? That's outside the visible spectrum. At least gives you an idea of the kinds of light we're talking about that you need to shine on these metals in order to release electrons to get this photoelectric effect. I was thinking about the cutoff frequency, but remember there was also these issues with the classical physics not really understanding or being able to explain this photocurrent and the stopping potential that they found, or the fact that the stopping potential is the same for different intensity lights. We can understand that now, right? Because the energy that's being given to these electrons actually doesn't have anything to do with the intensity of the light. The energy given from one photon to an electron is only due to the frequency of that photon. So that's why, regardless of the intensity of the light that's being shined on these metals, as long as it's the same frequency, they're going to have the same stopping potential, where the potential difference needed to stop those electrons from leaving the material is going to be the same. We can also actually understand why there's this plateau of the photocurrent too. So on the other side of this, right, we're increasing the voltage or the potential from that voltage source, and when we increase it, we're essentially adding now to the kinetic energy of the electrons that are being ejected. And classically, you would kind of think that if you just keep increasing that potential, then you can keep speeding up the electrons that are leaving, and this shouldn't really plateau the way it does. However, if we think about the light hitting those targets, those metals, as photons, right? It just like streams of these photons hitting the material, then there's only so many photons that hit that material at a given time, right? The intensity is just more photons, or a higher rate of photons hitting them. So it doesn't really matter if you try to add to the kinetic energy of the electrons. Whatever amount of photons are hitting, that's just the maximum amount of electrons you're going to be able to release. Higher intensity means, there's this higher amount of electrons you can release, but you can't get more out just by trying to increase their kinetic energy once they're released from the material. That is to say that the maximum photocurrent you're going to get is limited by the amount of photons that are incident on that target, or the rate of the photons hitting that target, not the intensity. Okay, now we have photons, right? Particles of light. And when you're talking about particles, a very helpful quantity is the momentum of that particle. But a photon has no mass. Classically speaking, it would have no momentum. It's a bit of an issue when you're trying to think about the particle-like nature of light, or the photon aspects of light. However, it turns out that relativity already gave us a way to interpret the momentum of a photon. If you recall, at the end of the last chapter's lecture, I showed you that the total relativistic energy of an object is related to its relativistic momentum and its rest energy. Right? Remember, mc squared was the rest energy. We can use that relationship in order to write down what a photon's momentum might be. So recall that the energy of a photon we could write in terms of its frequency. It's just h Planck's constant times the frequency of that light, frequency of that photon. And so relativity tells us that the total relativistic energy, that object, that photon, is going to be this. But now, right, the photon has no mass. This term is going to go to 0. So if we solve for, square root both of these sides and just solve for the momentum, it's just that total energy, relativistic energy, divided by c. And now maybe we can give that momentum a little f, that indicate this is the momentum of a photon with frequency f. And now that E, we're thinking about as the photon energy in terms of Planck's constant and its frequency. So this you can write as hf over c. And then given that, remember that frequency is related to the wavelength of this light in this way, that momentum, maybe we don't even need to write f anymore because we're talking about it in terms of wavelength. It looks like h over lambda. And then finally, if we want to write it in terms of this wave number k instead of lambda. K was 2 pi over lambda. So this momentum of the photon then looks like that. hk over 2 pi. Now, we are going to basically just incorporate the direction of the photon's momentum, its linear momentum, into k. We're going to turn k from a number to a vector and say its direction is, let's say it is parallel to the direction of the linear momentum of the photon. To do that, we can then write this as that. And then the last thing, I'm going to put, I mentioned in a class meeting that 2 pi shows up a whole lot, and so much so that we start incorporating it into variables. So instead of h, writing h bar, which is equal to h divided by 2 pi. Is that? So that's where we would get to this relationship for the momentum of a photon of frequency f being equal to h bar or h over 2 pi, times this wave vector now. We've sort of then gone from thinking about light in the classical picture as this electromagnetic wave with an amplitude and wavelength or frequency, to now this quantized picture of light as photons, chunks of light in a sense, and those photons have momentum.